Hello and welcome. This is going to be our lecture video for March 26th. I'm going to be talking about sigma notation today. All right, we'll start off with a problem that was on the last worksheet. We're asked to simplify this expression that has factorials in it. That's what all these exclamation points are. And what we know about factorials is that 93 factorial means 93 times 92 times 91 times 90 all the way down to 1. But it seems like this would take a long time to write them all out. So at some point, you can just put an exclamation point. And actually, I want to put it back here because everything from 89 down could be summarized as 89 factorial. All right, and then on the bottom, I won't expand this 89 factorial, I'll just leave it as 89 factorial. But I will expand the 4 factorial. And now the 89 factorial can cancel. And then this can be plugged into our calculator and we can see what we get. So 93 times 92 times 91 times 90. I press enter. I get a number in the 70 millions. It looks like. Then I'm just going to hit divide by, in parentheses, 4 times 3 times 2 times 1, close parentheses, hit enter, and I get 2919, so 2,919,735. Now, if you tried to plug this directly into your calculator, it wouldn't work because 93 factorial is actually too big for your calculators to do. It's only after we simplify it that we're able to get a number that we can actually get out of our calculator. All right, expressed in factorial form. This was again on the worksheet. 6 times 5 times 4 times 3 times 2 times 1, that is 6 factorial. All right, all the numbers less than 6 being multiplied together. 10 times 9 times 8 times 7, but then it stops. Well, I can get a whole stack from 10 down to 1 by doing 10 factorial, but then how do I get rid of everything past 6? I have to divide away 6 factorial. So this is equivalent to that in factorial form. Common mistake would be to put the 7 down here, but then this 7 would actually cancel. We want to cancel everything after the 7, so that's why we do a 6. So those are those two answers. One more from the worksheet, 2 times 5 factorial over 2 factorial times 3 factorial. So I'm going to start to expand the 5 factorial, 5 times 4 times 3, but then I'll stop there and put the factorial. I'll expand the 2 factorial, that's just 2 times 1, but the 3 factorial I'll leave as 3 factorial so that can cancel there. This 2 would go on top, but it can cancel with that 2 there, and all that's left is 5 times 4, which we know is 20. All right, so that might have been a little bit of overkill. You could have just plugged this one into your calculator, but it's good practice to practice all the canceling. All right, one more from the worksheet. We had n minus 2 factorial over n minus 1 factorial, and we were asked to simplify this. Well, when we simplify this, we have to figure out which of these is bigger. And it's actually the one on the bottom. If I take any quantity and subtract 1, well, that's going to be a bigger number than taking that same quantity and subtracting 2. So this is the one that we want to back up. We want to rewrite that n minus 1, then subtract 1, and we get n minus 2 factorial. So we backed it up 1 by subtracting 1, and the factorial moves to the end. All right, now the n minus 2 factorial can cancel. I have to leave something behind on the top, so I leave a 1 behind on the top, and this simplifies to 1 over n minus 1 every time. All right, and now let's just do one where we're solving for n. So again, we asked which one's bigger. This one is bigger. So it's the one that we're going to back up. I'm going to make it n plus 1 times n factorial. I don't know this parentheses. All over n factorial. So now I've backed it up enough that it can cancel the bottom here. So cancels. This is still equal to 6. Get n plus 1 equals 6. Minus 1 minus 1, n equals 5. All right. Goal today is to understand how to write series and sums with sigma notation. Sigma notation is the shortest way to write out a long sum of terms that follow a pattern. So it's going to be pretty helpful in doing that. All right. In your notes, put today's date. If you want to follow along in your textbook, it's 392. All right, so a series is very simply a series is the sum of a sequence. So if a sequence is something like 1, 3, 5, 7, then the series would be 1 plus 3 plus 5 plus 7. And in this example, that evaluates to be 16. So series will often be able to be shrunken down to a single number. Sometimes they are infinite. But yeah, it's not like a sequence that is lots of numbers separated by commas. They're separated by addition symbols, and therefore everything can be combined. All right, so sigma notation. So let's do one big sigma notation. We'll label it in our notes. First thing we need is the Greek letter sigma. So here we go. This is the Greek letter sigma. We write it pretty big because we need to write lots of numbers around it. All right, on top of that sigma, we're going to see a number. This is the upper limit. If there is one, if there's not an upper limit, then we put an infinity up here. But if we are adding up a sequence with 6 terms, we put a 6 up here. All right. On the bottom, we're going to pick a variable. A really common one here is I, but you can pick whatever you want. And then you're going to set it equal to some number. So the I is going to be the variable in the problem. I think one of the reasons we often use I is because this is called the index of summation. And it is the variable in the problem. And then this number here, this is our starting number. So you're going to start by plugging this number in for I, and then you're going to keep increasing it by 1 until you hit the upper limit. All right, and then on this side over here, we're going to have the sequence we are summing. Let's say sequence. All right. So there's a couple of formulas that work with sigma notation. One is that the number of terms being added equals the n, the end point on top, minus the starting number. And it seems like that would get it because that's where we end, that's where we start. But you have to always add 1 or else you're going to be off by 1. So yeah, the number of terms being added is n minus the starting number plus 1. Okay. Another good one is if I am, do some different color, if I am summing a constant from I equals 1 to n, so c is just a constant here, we don't see an I anywhere in the expression, then my final answer will just be c times n. Alright, but most of the time we do put a variable in there. Here's another one. If I am summing some constant times a sequence, and I'll make that a sub n, I can bring the constant out in front. And let's make that clear what happened there. The constant can move out in front. All right, and one more. If I am summing, let's use a different color, two sequences that are being added together, a sub n plus b sub n, I can just sum them separately, the sum of a sub n plus the sum of b sub n, and then add the results. So essentially sigmas can be distributed to sequences. We'll write that. They can be distributed. Okay. So here's our first sigma notation with all of the numbers filled in. We can see this is our variable. It appears in the definitions of sequence here. Here's our stopping number. Copy it down just like as you see it there. Now let's start writing it out. So the first thing I want to do is plug in 1 for n. So this is going to be 1 to the 4th. Then I write a plus sign. All right, then wherever I plug this in, I'm going to increase that by 1. This is going to be 2 to the 4th. Plus 3 to the 4th. So I'm just going to keep increasing that n by 1. Plus 4 to the 4th. Plus 5 to the 4th. Plus 6 to the 4th. And here's where I stop because now n has been incremented all the way up to 6. So once n reaches 6, we're done. And we can solve this. I'm just going to do it in my calculator. 1 plus 2 to the 4th plus 3 to the 4th plus 4 to the 4th, 5 to the 4th plus 6 to the 4th. And we get 2,275. You can double check that on your own. Make sure you know how to plug it in. But yeah, as easy as that. All right. Here we've got one with 2 k's in the expression. And k is starting at 3 and ending at 7. So this here is going to be 3 plus 1 over 3 plus 4 plus 1 over 4. Notice both of the k's got increased by 1. Plus 5 plus 1 over 5. Plus 6 plus 1 over 6. Plus 7 plus 1 over 7. And then we stop because we've reached our ending number of 7. And now this can be plugged into our calculator. I'm going to do some of it in my head. So I'll make that 4 over 3 plus 5 over 4 plus 6 over 5 plus 7 over 6 plus 8 over 7. And we get 6.093 approximately. Let's see if I can turn that back into a fraction. It's exactly 853 over 140 if you get the common denominator. A little dot, dot, dot. All right. Here's another one. This one has an n on the top, so we don't see an ending number. How are we going to deal with that? So quick copy it down. Let's start plugging it in. The first thing I'm going to plug in for I is a 2. So I've got that this is 2 times 2 minus 1. maybe put a set of parentheses around that, plus 2 times 3 minus 1. But then what am I going to do? Because I could just keep going, plus 2 times 4 minus 1, but I'm never going to reach n. So eventually, I want to just say dot, 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 2 times n minus 1. So eventually the I just becomes an n, because we will reach the upper limit. We don't know what it is yet, but we're just going to keep doing this until we reach n. And then this can be simplified a little bit. 2 times 2 is 4 minus 1 is 3, so this is 3 plus, that is 5 plus 7 plus dot, 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 plus 2n minus 1. So this is a good way to write it. Yep. So your answer does include the dot, dot, dot there. All right, another one. Write out the sum for this one here. So only the k's are going to get replaced. X is going to stay a variable and it's going to stay in the problem. We're going to increment up to n, so that means we're going to have to use our dot, dot, dot. So this is 2 to the 0 plus 1, x to the 0, plus, so the x didn't change, it's just going to stay in x, 2 to the 1 plus 1, x to the 1, plus dot, 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 2 to the n plus 1, x to the n. And then we'll simplify that where we can. 2 to the first is just 2, x to the 0th is just 1, so this is going to be 2, plus, that's going to be a 4x, plus, let me get one more term in here, 2 to the 2 plus 1, x to the 2, so that becomes an 8, plus dot, 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 plus 2 to the n plus 1, x to the n. And that whole thing is our answer there. Generally, if you're going up to n, it's good to have like either 2, but probably 3 is preferred, 3 terms before you do the dot, 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 and then you just fill in the n's for your index. All right, let's go the other direction. We've got to write this sum with sigma notation. So first we got to figure out how do we get this sequence. Well, let's just kind of examine it. 1, 4, 9, 16, 25, 36. You might start recognizing this as perfect squares. So this is, 1 squared, 2 squared, 3 squared, 4 squared. So let me write it out like that. 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared plus 6 squared. And now I look and I see I've got this counting up by 1 behavior in here, so I can represent that with sigma notation because it automatically increases our variable by 1. So I want to pick a variable down here. I'll pick I, and I'll say we want to start with I being equal to 1, and we want to go all the way up to 6 of I squared. That way we plug in a 1 first, then we plug in a 2, then a 3, all the way up to 6, and we add them all together. So yeah, here's another one. Give you a second to copy it down. All right, so the endpoint here helps me out a lot because this basically is what my expression should look like. In fact, I could even use it, n plus 1 over n plus 2 as my sequence. Now I just have to figure out starting value and ending value. So what number do I have to start n at? So that I get a 3 here and a 2 here first. I have to start n at 1 because 1 plus 2 is 3, 1 plus 1 is 2. All right, and then I'm going to go up to, well, I'm going to go up to n. At this point, it's a little bit confusing. I need to change these variables because I can't have this be the same variable as this. But I want it to end with an n, so I'm just going to swap these out for something else, like an x. All right, now let me rewrite it. So x equals 1 of x plus 1 over x plus 2. And that way, we'll keep adding until we reach the end, and then we'll plug in the n. All right, you could have done I or A or B or something else, but I chose X for this one. All right, here's another one. This has got an interesting behavior of going minus, plus, minus, plus, minus, plus. A good way to get a sequence to do that is do -1 to the n. Because this here, when it's odd, it's going to be negative. When it's even, it's going to be positive. So this leads to -1, comma 1, comma -1, comma 1, comma -1. So if we include that somewhere, it's going to give us that alternating pattern. Now let's look at the numbers themselves. 3, 5, 7, 9, 11. It looks like we're just counting up by 2. So I can rewrite this 3 as maybe a 2x plus 1. The 5 could be a, well, let's not use x. Let's actually have it be a number so we can have it counting up. 2 times 1 plus 1. The 5 could be 2 times 2 plus 1. The 7 could be 2 times 3 plus 1. The 9, 2 times 4 plus 1. The 11, 2 times 5 plus 1. All right, now we can see which part is incrementing. It's that 1, 2, 3, 4, 5, and everything else is staying the same. So I definitely want 2 to the x plus 1 to be part of my sum. And now I just have to get that alternating behavior. So I'll do -1 to the power of n. But this would almost work, or I guess I better make it x, because I'm using x as my variable. Except for it would start us with a negative, because when x is 1, I would get a -3 here. So I need to put an extra negative in front there. And then let's see if we can simplify this. I guess this negative could be distributed in over here. And maybe we make this the sum from x equals 1 to, what's our last one here? 2 to the 6, 2 times 7 plus 1. So from x equals 1 to 7 of -1 to the x times -2x minus 1. And try plugging in different values for x, we get this exact sequence back. Okay, that one was a little bit tricky. One more we've got with just x's going up to 6. We've got some alternating, so I'll give you a quick second to copy this down. All right, now let's write out the sigma notation for this. Let's see if we can just see what's going on here. So we can think of this as an x to the 1 here, so that we go 1, 2, 3, 4, 5, 6. So it really looks like we're going to go from I equals 1 to 6. All right, and now we can fill in an over 1 factorial here, because that's just equal to 1, it's not going to change anything. And over 0 factorial here, because again, that's just equal to 1 and isn't going to change anything. So let's see. I can do it as a big fraction, x to the I on top. And then on the bottom, I need to do, in parentheses, I minus 1 factorial. Because if I plug in a 1 there, then 1 minus 1 is 0, then 1, then 2 all the way up here. Last thing is I need to get that alternating behavior. So I'm going to multiply this by -1 to the I. And I guess I can move this negative up to the top over here. So that it's just in a less awkward spot. or leave it there. Anywhere's fine. Okay, got that one. And you can always double check by just starting to plug in numbers for I and make sure we recover this sequence here. All right, you've got a worksheet to work on. That's all for this lecture. Have a good rest of your day.